Alright, so this is a video that I'm making pretty much for myself to get a better idea of what circuit elements are. This is an auxiliary video for EE16A, which is a class I'm currently in. I'm not making this video, well, I'm not an EE16A staff, so this is like a private video, blah blah blah, and I'm pretty much just gonna run down my thought process on some of these circuits, um, and to pretty much get a better idea for myself. I'll probably end up watching my own videos in the future, but the reason why I'm posting these videos is just to maybe help others out there. Maybe you're struggling in the class as much as I am, or maybe you have a similar thought process to me, or maybe you're just lost and you know you're trying to get as much help as you can. So let's just jump right in. And first, we're going to talk about basic circuit elements. So I'm going to assume that you already know the basic circuits units. So the basic circuit units, and those are voltage, current, and resistance. That's it. Just these three. And their units are volts, amperes. So this is represented by A. This is represented by V, and resistance, which is in the units of ohms, which has this little horseshoe-looking thing. Okay, so the basic circuit elements. There are, so far in class, we've talked about the wire, the resistor, the open circuit, the voltage source, and the current source. So, of course, these are all ideal elements because we're in a class, and in most science, the real world is not what really happens on paper. So let's just talk about a wire. So I have a wire. So wire is just pretty much what you think it is. It's just like a piece of metal that conducts electricity. And in note 11, they say that we symbolize a wire like this. Now, does it have to have these dots on it? No, but pretty much it's just like a line. And then, of course, we need to assign units to it, aka the current and the voltage. And so we're going to say, okay, there's an I element to this wire. Actually, let me see I wire. It's the current of this wire. The current of this wire. And then there's also a voltage. So there's a voltage of this wire. And pretty much we assign a flow direction to it. So the flow direction, we pretty much just use an arrow. I don't know really why we use an arrow. Honestly, we could use, I don't know, a stop sign or like a green light, red light thing. You know, a green light, a red light, but that doesn't make any sense. So we actually just use, we just use a arrow to signify direction, and this direction is just arbitrary. So you can just put it, this way. You could have written it the other way as well, like this, but it doesn't really matter. Oh, and we don't really use this tail just because the tail doesn't really tell us anything. And pretty much, based on passive sign convention, we're supposed to write a plus on the tail side of this arrow and a minus sign. And all that means is, in our arbitrary world, if it's the case that current is flowing in this direction, our voltages would follow this kind of plus minus pattern. And so if we assign the arrow the other way, our voltages would be, or based on passive sign convention, we would assign a minus or a negative on this side, the arrow, and a plus. And it might kind of seem weird or kind of dumb why we would do this, but the whole point of these this plus and minus is so we know the voltages based on the current direction. So if the current is flowing this direction, then everything would be reversed. If the arrow is flowing the other way, then we would kind of just flip the signs. And this is all arbitrary. When you truly solve for elements in a circuit, everything will work out as long as you follow this convention. You can kind of prove it, but I'm not going to prove it because it's just way too much work. So, now, in the note, it also says that V element, or in our case, V wire, is equal to 0. What the hell does that mean? Okay, I didn't know what that meant at first either. Why do I keep putting element? And I wire is a question mark. Well, all that means is there's this current, so the I is current, which is kind of the amount of electrons that are flowing through across this wire. So I is amount of electrons, or I is amount of electrons. So if we think of this as the number of electrons flowing through this wire, then the amount of electrons flowing through here is an arbitrary amount. So that's why we kind of put this question mark. We don't know what it is. It's based on something we don't know about that this symbol cannot describe. Or, yeah, this symbol as of yet can't describe. Now, why is V wire equal to 0? What the hell? Why is it 0? Well, V volts is really a representation of potential. And what they mean by potential is, in my mind, I like to think of it as energy. So if we think of a current, as like water, we think of, I like to think of like a river. So imagine I have a river, and I got some water flowing through it. Now, if the amount of water would be represented by I, so I would be amount of water. I don't like this color. Yeah, this color. So I would be water, and so current would be amount of water. Would be amount of water. And then, because I would be the amount of water, then V, in my mind, would be the potential of this water, so aka the energy of that water. So this drawing is kind of weird, but I like to think of it as, well, if we can think of this wire as a river, across this small sectional piece of the river, is there a change in the amount of energy that this water has? No. However, if we added obstacles, or we added like height drops, okay, then there would be a difference in the amount of water, or the energy of this water, which is, I forget, is represented by V. So V represents energy of the water, or energy drop. So because this wire, or this river, doesn't have anything else in it, there's no energy drop in the water. Now, this is also a very weird analogy, but in my mind, this kind of makes sense. If the river looked kind of like this, looked more like a waterfall, okay, then now there's an energy drop. This has high energy, this has low energy, so this would have high energy, that would have low. But this is a wire and has nothing in it, so it would look more like this. And that's what I like to think about. So when they say V wire is equal to 0, they're really saying there's no energy drop, or there's no potential drop, or energy potential drop. However you want to think about it, there's no drop. So if the voltage right here was 100, let's say the energy was 100, so we say voltage was 100, then the voltage right here would also be 100. There's no drop per se. And so that's what I kind of like to think about it as. Moving on. So now that we kind of understand why Vy is equal to 0, I'm going to move on to a resistor. So the way a resistor works is it's represented. So we have a resistor. The way a resistor works is a resistor is a piece of metal that causes a voltage drop. In other words, imagine I had this piece of metal and there was this like kind of weird chunk or barrier. Actually, let me just say there was some barrier. Say some barrier or obstacle. Some area or obstacle. We have some barrier or obstacle. Then we apply a voltage, so like a voltage and a current flowing in this direction. What happens is this barrier or obstacle causes a voltage drop. And the reason why it causes a voltage drop or energy drop is that energy will be spent going through this barrier or obstacle. So you can imagine if I think of a river, or maybe not a river. Let's try something else. You can think of we probably think of a river. Yeah, let's just think of a river. So if we thought about a river, and we kind of just throw some rocks in here. Throw some rocks. But instead of a river of water, we say it's a river of people. And as the people go through here, go through these rocks, it's a river of people. So just imagine a river of people. And let me color these rocks. Say this rock is a red rock. Red rock. It's a river of people. These people will spend energy trying to move through these rocks. They will spend energy trying to get through these rocks. Spend energy moving through this rock. Through these rocks. You can kind of think of it like school. You can kind of coast through school. However, when you got a big test, you spend a lot of energy on the test. That's the way to kind of think about it. If I was just moving along through school, kind of coasting, my energy is kind of at a constant level. However, if there's a big test, it's a barrier, it's an obstacle, I'm going to spend energy on that test. And as a result, after the test, my energy is all spent. I'm tired. And you can kind of think of this as an obstacle, or a resistor as an obstacle. And the way we represent this is with this funky looking thingy-mabob, yellow thing. That is a bad color. Let's go like this. It's the yellow of this green. The yellow of this green. And that's called a resistor. It's some different metal barrier, something that forces the electrons to waste energy trying to move through this thing. And as a result, there's a voltage drop. There's a voltage drop. A voltage drop as a result. And so that voltage drop can be represented in the equation of Ohm's law. It's called V equals IR. So imagine if I had a kind of like a voltage right here. Let's say I had a voltage of 100, and then I had a voltage drop. So I had a V drop of 20 because I wasted 20 energy trying to get across this resistor, and ultimately I would end up with 80 volts at the end. So that's what you can kind of, or that's what I like to imagine a resistor as. It's some obstacle, some barrier that causes me to waste energy. So when we look at a circuit, usually we'll draw a circuit real quick. So if I just drew a circuit like this, there's this kind of resistor, weird looking thing, and we have our voltage source. Our voltage source. Let's just call this a resistor. Actually, not a resistor, just call it R. In this situation, if my current was moving in the arrow in the direction like this, these can be arbitrary. So in theory, you could, well, not in theory, you could assign the arrows the other direction, but I don't want to. I'm gonna do it this way. And following passive sign convention, my plus would go here, negative, minus, and a plus, and a minus. Okay. And the reason, well, yeah, so every element gets its own arrow. The reason why we don't have to kind of assign, I mean, we could, the reason why we don't have to draw another arrow like that is because this, as previously iterated, this is a ideal wire, because that's usually what we talk about in class is ideal scenarios. This wire doesn't really do anything to voltage or current, so I don't really have to draw these arrows. So this is unnecessary, can't spell, and unnecessary. So the arrows are kind of unnecessary, so I don't really have to draw them. So now that I've drawn the circuit, if I can imagine that, let's say my voltage source was, I don't know, 5, and this thing had a resistance of 2. And just believe me on this, that we have a current, what is that? A current of, we had a current of 2. So we had a current of 2 amperes. Yeah. So let's just say we had a current of 2 amperes. We don't really know why we have a current of 2 amperes. Let's just say we do, and hopefully you'll know why we have a current of 2 amperes. But so let's say we have a current of 2 amperes. We have 5 volts, and we have 2 ohms. As this current kind of flows through this pattern, the pattern that we've created, what happens is it wastes, or energy is spent moving across this resistor R. And the way we represent this resistance, or the resistor value, is 2 ohms, and that's just some unit that I don't really care about. And so as it moves across this resistor, in class we learned that we labeled this as the ground node, which has a voltage value of 0. But going in this direction of this white arrow, aka this direction, we have a voltage of 5. But what happened? Well, the resistor right here caused all the current moving through here, which is the flow of electrons, to lose its energy so that it's some zero. Now this is, you know, in this ideal-ish scenario, but this is kind of what it means. We move up, our current flows up here, moves down, boom, it loses all of its energy moving across this resistor, and then it comes back over here and now has kind of this zero energy value. Yeah, that's pretty much what a resistor is. It just causes electrons moving through it to lose energy. So if you can imagine, if we had higher resistor values, imagine we had 3 ohms, we'd have 4 ohms, we had 5 ohms, etc., etc. Based on the V equals IR equation, in order to keep this voltage up, we would have to increase the current. So if we wanted to keep this 5, we have a voltage of 5, and we have some arbitrary current. If we keep jacking this resistance up, current is supposed to go down. Yeah, sorry about that. Current is supposed to go down. So as this goes up, this goes down. So they have an inverse relationship. Inverse relationship. And that's pretty much what a resistor is. That's just what I like to think about it as. And the symbol is just kind of weird. We have the arrows. So yeah. So an open circuit. So what the hell is an open circuit? Well, open circuit. Well, an open circuit's pretty much what its name implies. We have this open thingy. There's some open space. Don't be scared of it. It's an open circuit. You can kind of draw a smiley face right here. But anyways, an open circuit is, as its name implies, it's open, and it doesn't really mean anything to us as of right now. But we do know, because it's an open circuit, that we actually don't have a current. You can think of it as in terms of a river, like earlier. If we had a river, and it just kind of stopped, but it continued right over here. I don't know how. It's probably some magical river. There's no current flowing through here. There's no flow of water. And you can think of it like, or also as a bridge. If you can imagine a bridge, I don't know if you've ever experienced this, but there are some bridges that actually raise up. So if you looked at a bridge, there's sometimes some bridges that look like this. I can't really draw. There's sometimes bridges that look like this. But what if I just broke the bridge and made it look like this? And, I don't know if y'all have observed this before, but sometimes there's bridges that kind of break in half so then ships can move under them. So ships can move under them. Well, that's pretty much what our open circuit is. There's no flow. Well, in the bridge scenario, there would be no flow of people. There'd be no flow of people across the bridge. So you can think of you can think of the open circuit as a broken bridge, and so current would have to be 0. Now, even though current is 0, that doesn't mean voltage is necessarily 0. Remember what voltage is. Voltage is just the measure of energy drop. So imagine if I had a voltage of 100 and a voltage of 80, there's still a voltage drop across these two wires. And so voltage is in question. Did not mean to do that. And we also have voltage source. So so now that we know kind of what resistor, an open circuit, and an ideal wire is, what about a voltage source? Well, You can think of the voltage source as something that looks like this, or if you've seen it in the diagram or in lecture, it kind of looks like this. There's like some resistors that look like that. Maybe another resistor that looks like this. But pretty much, this battery-looking thing is the voltage source. So that's the voltage source. And we can assign a current that flows this way. We can assign a current that flows that way, and we can assign the plus minuses in the corresponding, directions. But that's pretty much what a voltage source is. Usually or so far, sometimes there's like a value like 10 volts or 5 volts, 2 volts, etc., etc. But that's pretty much what a voltage source is doing, is it's adding a voltage in a particular direction. So, or it's adding voltage to our circuit. So, for example, in this situation, if we think that this battery or voltage source is adding voltage, then at this point, or it's adding a value of 10 volts, then at this point we would have 10 volts. And as we move across this wire, we'd still have 10 volts. And we'd still have 10 volts over here, and 10 volts over here. Because this is still a wire, and nothing really changed about it. Now, do not think of voltages in the same way as you think of current. Because current is the flow of electrons. So flow can actually be diverted. So if I imagine I had a circuit that looks like this, or look more like this, then current would actually be different across this resistor. Current would be different across resistor 1 and resistor 2, because if you think of it in terms of electrons, the amount can be diverted, but the energy can't. So if you're thinking of voltage as kind of energy, you don't really drop energy when you divert it. So it is kind of a confusing idea, but think of like 10 people. So imagine I had 10 people. 10 people. 5, 3, 6. Well, 2, 4, 6, 8, 9, 10. If you imagine I had 10 people, and I split them into, and let's say they had an energy level of 9,000. So they had energy level of 9,000, which would be our volts. Well, if I split up this group into, let's say, group 1, and I split the other group into group 2, so if this was group 1, this was group 2, does their energy level change? No. So as taking this as an analogy, if we apply this analogy to our circuit, if we have a bunch of electrons flowing here, and we have a bunch of electrons flowing here, the energy level does not change. Okay, it does not change in this part. Now, after they go through the circuit, they're going to waste some energy going through it. So, their energy is probably going to be different over here and over here. But, that's another story for another day. Or, not a story for another day, but we've already discussed what the resistor does to their energy. And correspondingly, if we had R1 right here and R2, they would lose energy based on those R values. Now, in this situation, in this white diagram, does current change? Applying this analogy. Yes. So if R2, let's say, was equal to 5, and R1 was equal to 5, aka the resistance is the same, the number of electrons that flow through here and through here would be equal. But even though they're equal, we still separate the group in half. So like if you can imagine, yeah, so if you imagine in terms of these people, although their energy level hasn't dropped, their current or their numbers have dwindled. And I guess that's kind of the way you think of current and voltage in a circuit diagram or a circuit. And so the last thing we're going to talk about is what about current source? So if we have current source, what about current source? So current source is pretty much telling you your number. So the amount, not the energy level, just the amount. So if you can imagine, this is what's written in note 11. It's called current source, which is IS, and we have an I element and a V element. Well, this value, the value associated with this, just tells us the number or the amount of electron flowing through here based on some value, which is amperes. If you thought of this in terms of people, well, this would just be like, oh, 10 people are flowing through here. 10 people are flowing through here. So, yeah, that's pretty much it. But there's also a kind of a weird idea, which is why do we still have a V element here? Well, we haven't learned it in class yet, so we don't really understand what happens to a voltage when it goes through a current source. But I can assure you, there's, well, I can't really assure you. I don't really know what happens, so we're just going to have to find out what happens to that. But that also explains why V element, it would be a question mark, and I element is equal to IS, because the current across a wire doesn't change. So if this current source is stipulating a current, then I element must equal to IS, because it's not changing. This I element must be the same as this whatever's flowing through this wire, and this wire is stipulated by the current source. And V element, well, we don't really know about V element across the current source, so we kind of just put it as a question. We don't really know. I don't really know. Maybe you can go ask. Someone can go find out for me. Or maybe I'll go find out. But yeah. Thank you.